You may be familiar with the classic problem of three bugs on a triangle chasing one another, but today we are going to top it up a notch and see how we can put our knowledge of vectors to test when these bugs are caught in a crosswind that constantly pushes each bug sideways. Let's review the problem statement. Three bugs take off simultaneously from the corners of an equilateral triangle of side L. Each one is programmed to chase the next. So A chases B, B chases C, and C chases A, always with the same speed v. But there's a twist. A steady crosswind introduces a sideways drift perpendicular to the direction of the chase. So the actual velocity becomes a sum of the velocity with which they're chasing each other, which is v chase, and lambda times v chase cross k hat, where lambda is a constant tunable parameter that sets the strength of the drift, and k hat, as we had established earlier during our study of vectors, is the unit vector along the z-axis which points out of the plane given our choice to portray the 2D coordinate system with x and y axis on the screen plane. So the bug can no longer move directly towards its target, it gets nudged sideways as well. So this sets up our big question. Will the bugs ever meet? If yes, then when? And is there a condition that guarantees their meeting point? Perhaps it would be best to first try and understand how the motion occurs in the simplest case where lambda is 0. That is, there's just a game of pure pursuit with no wind present. So at every instant, each bug is directed straight to the next with a constant speed v. Let's see how this works considering small step sizes or time intervals. The bugs move a bit closer towards the next, and while the line of motion between them keeps changing, they always stay on equilateral triangles which shrink and spiral in with each frame, eventually collapsing to a point where the three bugs meet. This point is the geometric center of the triangle, which one can deduce from symmetry and is also called the centroid. You can see the full spiral paths of each bug traced here. Isn't it so remarkable and perfectly elegant? How such neat spirals appear out of what may at first have looked like seemingly chaotic motion? And it's time to understand how these spirals aren't accidents of motion, but a pure result written into vectors themselves. Let's analyze the setup we already saw for lambda equals 0 and try to solve the problem for this case using the concept of vectors. In case you're unfamiliar with how vector operations work, you can check out my videos on the same from the pop-up on the right up here. Okay, now once again here's the spiral path with the exquisite geometric pattern. If we pick one of these frozen frames, this triangle right here, note how the motion is the exact same as the original triangle owing to the symmetry. You can see in both cases the angle a moving bug makes with respect to the centroid is the same pi by 6 radians or 30 degrees. Now, how do we find the time it takes each bug to meet? We have a simple way to do that without overwhelming ourselves with these curved paths thanks to how vectors are defined. We can obtain the displacement vector from the bug's starting and end points, given the nice geometry of equilateral triangles, and we can also obtain the bug's velocity component towards the center. So we have the vector RBO, which is the displacement from B to the centroid. Let's break it into its components so we can obtain the displacement in terms of the side L of the triangle. From the triangle's geometry, we know that the angle between BO and BC is 30 degrees. So the component of RBO along BC is cos 30 degrees or the square root of 3 by 2 times RBO, while the perpendicular component is sin 30 degrees or half times RBO. Now the parallel component of RBO is equal to half the length of the side of the triangle, which allows us to obtain RBO in terms of L as L by square root of 3. As for the velocity, the bug B moves towards C with a speed v. But what we require is the component of this vector along the displacement vector towards the centroid. So we obtain that component through a dot product between VB and the unit vector along RBO, obtaining square root of 3 over 2 times V in the direction of R hat. So we have everything now to obtain the time. We just divide the displacement RBO by the velocity component VBO, thus obtaining T equals 2L by 3V. So we have solved the minimal case of this problem, one that appears in standard books of physics, be it H.C. Verma or Irodov. There is also another way to solve this problem for this minimal case that may appear short and clean by using the concept of frames of reference and relative velocity. We haven't covered the basics of kinematics yet in this series, so if it feels like a shortcut or not convincing enough, don't worry about it as we still have the vector-only method to our aid. Still, I feel like this is a nice solution we must explore and also a good time to briefly introduce some concepts. So, say we fix our point of view on one of the bugs, say the one at C. So we are seeing the world from C's point of reference, thus C appears stationary while the triangle moves around it. From this frame, bug B is still chasing C, and because C is stationary in our view, we only care about how fast B approaches C. Now, what we are concerned about is the relative velocity of approach of B towards C along their line of contact BC. If we resolve bug C's actual velocity, which is towards A with a magnitude of V and hence at an angle of 60 degrees to the line BC, we get V sine 60 perpendicular to BC, and as for the projection along BC, which is what we require, it is V cos 60 degrees or V by 2 towards B, that is in a direction negative to C, as though it's moving away from B with a speed V by 2. So the relative velocity of B with respect to C is V minus negative V by 2, which is 3V by 2. Thus, the distance between B and C closes at this speed. From this, we can obtain the time t as L over 3V by 2 or 2L by 3V, which is the same result as before. To further convince you that all three bugs do indeed meet at the same time, let's also look at the motion of A relative to C. This time, we observe along the line CA, about which we should resolve the vectors. So, decomposing A's motion gives us a component of V by 2 towards C, and C's velocity is V along this line towards A in a negative direction than that of A. So, the relative velocity of A with respect to C is 3V over 2, so the time of convergence, we confirm, is 2L over 3V. What's happening here is subtle. Even though the bugs do have sideways components in their motion, those don't change how quickly they close the distance between each other. Only the part of velocity along the line joining them matters, and the sideways components are only responsible for the line of collision changing with time, leaving just the head-on pursuit. If you still can't wrap your head around it comfortably, that's totally fine. This will get easier to grasp once we move on to kinematics. Finally, we are ready to solve the actual problem where steady crosswinds are present, that is when lambda is greater than 0. As noted in the problem, the actual velocity is given as the sum of two parts, the chase velocity, which we are already familiar with, and the drift velocity proportional to the cross product of that with k hat. What the latter essentially does is rotate the velocity vector by 90 degrees clockwise and scale it by lambda, so the bug gets deflected sideways instead of heading straight towards its target. And this sideways drift increases as lambda increases. The magnitude of this resultant is root over 1 plus lambda squared times v. So as expected, the bug is now going faster, but also not directly towards its target anymore. Let's see what happens when we animate this over 2 steps. The bugs move along curved, skewed paths a bit outwards, and the question remains if they go inwards after a few iterations. Despite that, let's note the symmetry of the triangles that form. Now, just like before, we look at bug B and its motion towards the centroid O. We draw the displacement vector RBO, whose length remains L over root 3 from our earlier geometry, and we also know the actual velocity vector of B, the purple arrow we just saw, and we want to project it onto the direction of RBO, just like we did in the case when lambda was equal to 0. Now, this is where trigonometry helps us out. The angle between BC and RBO is 30 degrees, and we let phi be the angle between the purple vector and BC. Using the identity of cos theta naught plus phi, we can resolve the velocity component VBO, which turns out to be V times root over 3 minus lambda over 2. It is now clear that as lambda increases, the component shrinks and the bug is losing its ability to head towards the center. Then comes the final step. The time to reach the center is just the displacement over this effective velocity, which thus gives us t equals 2L over root 3 times v times root over 3 minus lambda. As you can see, the expression only makes sense for lambda strictly less than root 3. If lambda equals root 3, the denominator becomes 0 and the time thus becomes undefined. That is our critical threshold, and for any lambda that is greater than root 3, the time becomes negative, which in physical terms means the bugs would have met in the past but no longer can. They spiral forever, always chasing, yet never meeting. Let's finally watch how the system behaves for different values of lambda and appreciate some cool geometries. First, the classic lambda equals 0 case. Now let's add a little wind, so lambda equals 0.5. The spiral still closes in, but now the triangles skew slightly with each step. Now lambda equals 1. The sideways push is stronger now. The bugs are still trying to reach each other, but the spirals stretch out and take more turns before finally collapsing inwards. So you see, even when the magnitudes of the chase vector and drift vector are equal, the bugs still do meet at the centroid. Now at the critical value lambda equals root 3, this is where the denominator in our formula vanished. As expected, there is no convergence. The bugs keep spiraling in a warped spiral, but they never meet. They stay confined to a fixed orbit, stuck in a strange dance, forever chasing without catching up. And for lambda equals 2, well, things diverge. The bugs shoot outward and their paths curve away more and more dramatically with each step. They keep chasing, but the center becomes unreachable. It's a futile pursuit. And there we have it. From the elegant spiraling triangles to the twisting paths under crosswinds, we have solved this entire problem geometrically, analytically, and intuitively. So the next time you come across a question like this on a JEE paper, maybe disguised as one of those paragraph type questions, you'll know exactly what to do. And now that we have chased down every piece of this puzzle, it's only fair we let someone else do the chasing for a change. Anyway folks, that's it for today. See you next week. Subscribe to Eigen Akademie so you can have fun with more puzzles and master concepts with growing confidence, and share so you can experience the joy of learning with your friends. Ciao.